So, good morning, everyone. Thanks a lot for coming. And this is going to be storage systems, the old, the new, the overlooked, kind of a hardcore introduction into the storage systems. So, yeah, let's get started. My name is Alex. I'm very glad to be here. Probably the only applicable credential here is that I'm an Apache Cassandra committer and a PMC member. Been contributing to Apache Cassandra for a few years by now, and today we're going to talk about the storage systems. You definitely heard about LSM trees and B trees quite a few times, and after a few repetitions, it might start looking as if all the storage systems fall directly into one of these categories, or then that there is even such a strict distinction, so like one or the other. Today we're going to talk about the concepts and approaches for storage engines for which it's hard to say whether they're more LSM or B trees or something entirely different. So we'll dig into some of the important yet less widely known algorithms and concepts which are useful and applicable, and we'll discuss some of the more novel or new approaches, some of which are gaining more and more popularity these days. Main motivation for this talk is to help everybody to learn more about what's going on in the database community and widen everyone's horizons about the database storage. So it's kind of like less introductory, but more like what is going on and some of the more interesting things. Some of the algorithms I'll be talking about today are already widely used and commonly known, and some have only implementations done by the researchers. So like it's not something that you can take off the shelf, plug in, and start using today. I'd like to think of this talk as a conceptual one, so you're going to be learning about the foundational concepts that never grow old, rather than be able to grab these concepts, go ahead and apply them straight away in your work. And we're going to be skipping through specifics of each algorithm because it is impossible to elaborate on each one of 10 algorithms in 45 minutes of time. So since we're going to be talking about the trees in databases during this talk quite a lot, it's worth mentioning that we concentrate on the disk-based ones and not in-memory ones. So we are not going to be covering the in-memory databases at all. So this is not applicable to those. One of the things I found interesting when reading a bunch of papers about storage systems is that most of them seem to have strong opinion about one of the three concepts. So it's either ordering, buffering, or mutability. When you go out of this room after the talk, these are three directional vectors I would like you to remember: ordering, buffering, immutability. It seems like combining and putting accent on one of these properties sets the direction for both the design characteristics, both design and characteristic of the data store. We'll talk about more detailed definitions in the scope of related data structures, but I think that these words should be already familiar for anybody who's worked with data infrastructure software for some time by now. So ordering defines whether the data is stored in lexicographical order on the disk. So whether it's been sorted before it was put on disk or not. In other words, the keys that are closely sorted together will also be stored closely together. So sorted together, stored together. One dimension to ordering is that whether or not you can scan the range of the values rather than just grabbing one value from the database. Buffering here defines whether or not we have to collect a certain amount of data in memory before putting it on disk. So certainly every on-disk data structure has to use some buffering. Well, or we all use buffering to some degree. By that I mean that we are using like block storage, which means that we are transferring the data in blocks. So we have to buffer at least a block. So when we say buffering here, we don't mean like operating system buffering or like this block buffering, but we are talking about something that avoidable theoretically and something we deliberately choose to do. So we are choosing to buffer a, well, non-trivial amount of data in memory. For example, like buffering we are used to like LSM trees, like Cassandra does, or RocksDB does, like with mem tables and stuff. And finally, we have mutability or immutability. And by this, I don't mean the concept which is coming directly from functional programming, or it's like similar but yet different. So we're saying that files are immutable on disk, meaning that we do not change the data in place. So we don't go to the middle of the file and start meddling with whatever we have written already. Often the distinction between LSM and B-trees is drawn as, okay, immutable versus in-place update storage, but you will see that there are a few algorithms that are undeniably B-trees, but are immutable. So let's start with the ground zero and everybody's favorite, B-trees, which should explain why we should even want to have alternative to them and why we need these three concepts which are like in different combinations. So first and foremost, I like to think of B-trees as a page management algorithm. It allows us to compose, place, and navigate through the pages on disk. Since many algorithms we'll going to be talking about today are, well, B-tree derivatives, the B-trees that we're going to talk about over the next couple of slides are B plus trees. So whatever you're used to have in like SQL Server, or MySQL, or Postgres, and many other more or less traditional relational databases. B-trees have some like in-memory siblings, like 2-3 trees or red-black trees, and B-trees are different in two things. And these two things make them very good as a non-disk data structure. First, they allow each node to have hundreds of child nodes, unlike their other like in-memory siblings, which have only few child nodes. In other words, they have high fan-out. This helps to improve locality of the neighboring keys. So neighboring keys are going to be stored together and yeah, in the same page on disk. And because of this high fan-out, each individual level can hold more items, which makes the height of the tree smaller. This helps us to reduce the amount of seeks during the traversals. So when we go from the tree top to the tree leaf, we are making a disk seek only when we're switching between the levels. And the less levels we have, the less high our tree is, or more shallow that is, so to say, the less disk seeks we're going to perform. So two concepts, high fan-out and low height. Traditional B-trees were developed in the time when spinning disks were one of the most widespread storage medium, and this has put a significant influence on their design. On a hard disk drive, we could perform in-place updates. By the way, anybody knows what like in-place updates is? Okay. So yeah, we write to the exact physical location where the previous data item was located. So we pretty much overwrite the page. This in-place update stuff allowed B-trees to keep nodes mutable. So we can just find the node and overwrite it on disk. Each node of the B-tree, which kind of roughly translates to the page on disk, was usually 50% full on average. So we were wasting quite a lot of space since it was reserved for the future writes. Newer storage devices such as SSDs are different, however. In SSDs, pages cannot be updated in place since they have to be erased first. To make matters worse, you have an ability to write a single page, but you cannot erase a single page to rewrite it again. The smallest unit that you can erase on the SSD is a block, which is usually about 256 pages large. To mimic the hard disk and act as if we were able to replace the pages on disk, SSDs use something called Flash Translation Layer, or FTL. It is responsible for mapping the page IDs, like internal ones, to their physical locations, and like it tracks empty, written, unwritten, like discarded pages and everything related to that. So it manages the page lifetime on disk. To erase and reclaim these written pages, the Flash Translation Layer has to perform garbage collection, which can cause like relocations, taking things from one place to another, and all sorts of other delays. So long story short, updating pages in place was okay, and we could live with it as long as the only downside was the fact that we had to reserve some space for the future writes. But if each page rewrite on SSD comes with a cost, we should consider some alternatives. So we should think how we can reduce the number of I/O operations and generate like less write amplification. But what exactly is write amplification and what causes it? Write amplification shows how many bytes we end up writing for every byte of data we'd like to store. You can define a space and read amplification pretty much in the same way. For every byte we read, how many redundant bytes we also read from disk, and like space amplification for each written byte, how many redundant or how much redundant information we end up storing on the disk. Now let's see where exactly this amplification thing is coming from. First and most obvious one, source of this write amplification is when we try to update the same tree node several times after one another, each update results in a write on disk. So in order to update a single key, we have to rewrite an entire page or node on disk, okay? The second source is everyone remembers that trees have to be kept balanced, right? So we have to balance our trees in order to minimize their height, because you remember that like the lower the height is, the better our like search characteristics is, because we will make less hops over the levels. And to keep the tree balanced, B trees are using concepts of splits and merges. These operations are infrequent because of the breadth of the tree, so each node has a bunch of children, so until we reach the capacity of the node, we still have some, I don't know, time or leeway. And we have to make few writes before we actually have to split or merge the node. But still, for each split or merge, we have to access the parent node and remap the children, and overwrite the split node and write the new one, and so on. So it's a bunch of like disk operations that we perform. Once again, this is not a deal breaker. I'm not saying that the only problem with the B trees is that the fact that they're doing splits and merges, but this is one of the contributing factors, and if we can avoid it, it would be pretty cool. And lastly, because of the multi-version concurrency and because it's cheaper to update the node contents without overwriting them each other in time or like resorting, erasing memory, and so on, many B-tree implementations are just appending stuff to the end of the page and then writing it, which can result to the fact that the node, even if it looks full, is in fact kind of half empty because it holds a bunch of garbage cells, and these cells are fragmented. To reclaim this space, we have to defragment and rewrite the page completely. And this operation is usually performed independently from the regular write path, and you may have heard about the compaction or vacuum process in different databases. It's called different ways. And this is one of the other factors that is kind of increasing the write amplification. So in summary, we have three sources of costs that we would like to eliminate. The costs which are coming from in-place updates, because we're not using the spinning disks anymore and they're not free, and they will cause more write amplification or will cause problems with random writes on SSDs. and from splits and merges, however minor their contribution might be, and from maintenance or like compaction or a vacuum, whatnot. In addition to that, we have a write-ahead log. In vast majority of the implementations of B+ trees, we have to maintain it for transactions and crash recovery. And let's just see what we can do about all these things. So it looks like we can use buffering, which is probably the most obvious thing to do, at least at the first glance. And we can fix all or most of or all of the problems that we just talked about. Write amplification from in-place updates, splits, merges, and the maintenance. So WiredTiger is a storage engine, previously an independent one. Now it's used in MongoDB. It comes up with a simple approach. Instead of updating the B tree page every time we perform an operation against it, let's put all the changes to the fixed size buffer that is in memory before we do that. Beam, bam, boom. Our job is done here. Everybody goes home. Everybody's happy because, well, we fixed the problem with the node updates, which got cheaper. Splits and merges got cheaper because we do not do them like every time, but we only have to do them on cache eviction, like whenever the node has to be evicted from memory and go back on disk. And we will do this whenever this in-memory buffer grows too big. So we can also almost completely eliminate the maintenance costs because we just made the disk writes very infrequent. So this is going to be like happening only every once in a while. So we can defragment the page and write it in, well, a good shape every time we do a write. So which is pretty cool. Another approach, which is rather similar to whatever we just talked about, is called LA trees. And I think that the full name is lazy adaptive trees. And they're saying, like, why instead of attaching a small buffer to each page, why wouldn't we take larger buffers and attach them to groups of pages instead? So it's quite simple and quite similar to whatever we just seen. One possible advantage of this approach over the previous one is that we can have a smaller memory overhead per node, since we're sharing the buffer between the nodes. And this is especially true for the cases when a number of updates per node differ significantly. So in the previous approach, we would have like one buffer to be like completely full, and we would evict the page, and the other buffer would be like almost completely empty, and like there would be like big imbalance between these two. And here we sort of can like have better control over it. We can also check buffers when we evict the page and pick the page which has the most of modifications in order to like free up the most of the memory. So these two things really help us to amortize the cost of the random writes that we do on disk. So far, so good. So buffering is helpful, but how about immutability? Turns out that we don't have to go all the way to like LSM trees to get immutability. We can just start with something much simpler. And let's start with copy on write B trees, because this is as close as we get to B trees themselves. This approach is used in LMDB, a storage engine on top of LDAP, among other places. And the main idea of copy on write B trees is that every time we write, we create a copy of the target page. Every node on the path from the root to this target leaf page is copied before on update. So every time we update, we just copy the whole thing. You can see this parallel structure or parallel reality in gray on the right side. As soon as this parallel reality is created, we compare. We use compare and swap for the root node and make the new reality kind of the only reality. So we formalize it or publish it, or just make it visible to the readers. And nodes are immutable, written once, never updated. They can only be discarded. Since we have a disadvantage, one of the obvious things is that whenever we do any operations, we have to copy a bunch of things, right? So we kind of amplify the writes, and since we already have to do that, why wouldn't we just use this for our own advantage, right? And one of the advantages is that the concurrent operations or things like multi-version concurrency becomes extremely easy, because whenever you have followed a pointer, you know that you will end up like however long you're going to be reading, you will be always reading a consistent database state, so nobody can yank it from underneath of you, and like it will be always consistent. And the other thing is that, for instance, LMDB allows having no write-ahead log, which amortizes a bunch of costs as well. And there are no like corrupt states of the database, no incomplete writes, no recovery on crash. So because like once we have written and published this new tree, this is the thing. I mean, we cannot go back in time. And this is pretty interesting and cool. So this is good, but what are the other ways we can use immutability? And maybe we should try combining immutability with the buffering. And this results into something completely different. We already know about multi-component trees and sorted string tables from, once again, Cassandra and RuxDB, which I have repeated several times over this talk today. We just skip like the traditional LSM trees. And if you are not familiar with this concept, you can check my last year's talk about the modern storage systems to learn more about these. I describe in a lot of details how they work. So interestingly, even though both traditional LSM trees, like multi-component LSM trees, and the two-component LSM trees we're going to be talking about today were mentioned in the same paper, almost nobody talks about the two-component LSM trees. So this is like one of the most overlooked things, in my opinion. And let's first define what LSM means. So LSM trees stands for log structured merge tree. And log structured here means that we have a file where we can only append the data. We can never go and start modifying the already written contents. We don't do random writes because we always write to the end of file. So they're often contrasted with B trees, where you have pages that you access during the read-write path and update them all in place. Instead of managing pages in log structure storage, you only have to point to the right location in the log. The two-component log structured merge tree work approximately in the following way. Instead of writing directly to disk, we buffer the writes in memory. As soon as memory base table grows large enough, we take its part, it's highlighted in black here, and flush it on disk and discard it. If there was a segment on disk that would fall into the same key range as the flushing in-memory segment, we just merge them together. So we take the in-memory segment and on-disk one, and they belong to the same key range, so they store approximately like same range of data. We merge them together, preserve the sorted invariant, and we write them on disk. So as the contents of in-memory and disk-based parts are merged, they're written on disk and are then attached to the place which was like previously published, like instead of whatever the contents of on-disk date file we kind of discarded or we just merged. It is important to mention here, so while merging in-memory and on-disk contents, we preserve the data sort invariant, so data is sorted. And even though it looks visually a bit like copy and write B trees, the approach is quite different. The advantage here is that we avoid the write and space simplification, which is coming from in-place updates. And when we're writing the merge tree contents, we write it fully packed with the data. So we don't reserve any extra space. So it's like fully packed segment of data, as compact as we can get. And because of the flushes don't happen very often, we can perform these merge operations relatively infrequently. And now our write amplification is coming only from rewriting. So whenever we have this new segment, we will take the same keys, write them again, and take the same keys, write them again. So the write amplification has changed its source. Before it was on the right path, and right now we switched it to this asynchronous compaction process. So now let's try another or slightly different approach, because we kept repeating B trees, because in all the concepts like B trees and log structured merge trees, we constantly evolve around the B tree concept. And if we kind of try to switch the focus to something slightly different, and let's just take a look at FD trees. So FD trees, called flash disk trees, consist of a small mutable on-disk tree on the very top and multiple immutable runs. So it's just kind of arrays of sorted data, once again, fully packed. As soon as the head tree fills up, its contents are transferred on disk by merging it with the first immutable level. And we continue this process. When the first immutable level gets too big, we merge its content with the second one, and so on and so forth. So the data is going to be gradually propagating from upper levels to the lower ones. This approach kind of limits the surface area of random I/O operation, since it is only required for the head tree. And yeah, this is the only part of the data structure that is mutable. And some people say that you can even try and use this part or do this part completely in memory, so you don't even have to have any disk writes while it's there. So FD trees are structured very differently from B trees. To maintain the pointers between the levels, FD trees use a technique called fractional cascading. Maybe you heard of it. Fractional cascading helps to reduce the cost of locating an item in multiple sorted arrays by adding shortcuts between the levels. These shortcuts can be made by building kind of bridges between the neighboring arrays, so between two levels, and we're trying to minimize the gaps between whenever we make a jump, we would like to have approximately same amount of data on the next level between the pointers or the kind of these bridges on the higher levels. Bridges are built by pulling the element items from the lower level to the higher one that don't already exist on the higher one, and then just adding a pointer to the lower level. The advantage here is that you can perform only log n steps to find the searched item in the top array, which is kind of binary search. But subsequent searches, like searches in different levels, in lower levels, are significantly cheaper because you are already starting from the closest match that you have already seen on the previous level. So, coming back to FD trees, it has several advantages. First of all, random I/O is limited to the head of the tree, and we have an ability to build these sorted runs with fractional cascading, in which have very low overhead and very nice performance characteristics. So it's one of the most interesting index types that I've seen so far. So now let's talk about something yet entirely different. Once again, we're going to be talking about Bitcask. If somebody heard about a database which was called or is called REAC, anybody? REAC? Yeah, it's cool. So it's also kind of an innovative approach to log-structured merge storage. Unlike the most log-structured implementations we've discussed so far, it doesn't buffer the data in memory and stores the data in append-only log-like files. Which means that the data on disk is not sorted, which is good or bad, we're gonna talk about in a minute. To make values searchable, Bitcask uses an in-memory hash table, which holds a reference to the corresponding latest or freshest value for each key. You can see that hash table on the left and gray arrow pointers to like latest key of these unordered data files. The old data might still be present on the in the files on disk, but is not referenced anywhere, and it will be cleaned up in the merge process, like compaction, which we already have talked about also. To collect the old values, Bitcask is using this compaction process, and it is just taking the two files and tries to merge them and rewrite them completely without ever trying to sort them again. One of the advantages here is we don't need to keep another log because, I mean, we already store the data directly in the log file. And writes are also super simple. You just append the value to the log, update the pointer in the hash table, and you're done. The write amplification here comes only from compaction, and because of the fact that we migrate keys several times and they can survive like again and again from one merge to another. Unfortunately, Bitcask data size is limited by like how many keys you can store in memory, and its pointer table has to be rebuilt on the startup. And also, it doesn't support the range queries. So there is a researcher database which is called Whiskey, and it is trying to solve the problem which Bitcask has without having any disadvantages. So it does that. It does improve on the Bitcask approach by providing a sorted key-only index that holds pointers to these unsorted data files. This can help us to decouple the sorting from the garbage collection, so data files can be compacted independently from the merge process of the immutable B trees, which is like kind of an index data structure. Both approaches reduce the write amplification caused by writing stuff into the log file in addition to keeping a primary data structure, and reduce the write amplification on the write path. And probably my favorite data structure is buzzword trees. So BW trees or buzzword trees. And it combines both, best of the both worlds, you can say, and it combines the LSM storage and B trees in a very interesting and novel way, in my opinion. So the BW trees store the base node separately from its modification. So the base node is just like the beginning, like the first value in your B tree node, and all the modifications are called delta nodes. And they form a list from the base to to modifications. So you have the most recent modification pointing to less recent modification, and then several steps later you get to the base. So you can see on the slide the dotted lines. So these ones, they represent kind of in-memory virtual links between the nodes, and the nodes are not stored together on disk, but one part of the node can be in one part of the log file or log of the file, and the other one can be in a completely different place. So in order to reconstruct the node, we have to follow several pointers on disk in order to get them back together. And the solid lines represent kind of pointers from one place on the disk to the other place on the disk. Interestingly, updates are stored in the log-structured file or log-structured data structure. and it's called llama in short. So it's like log-structured, access method-aware data structure. So the BW trees combine the best properties of the both worlds. We get nice write properties of LSM, minimal read and write amplification, yet we have pretty good read time performance. Because of the log-structured nature of the underlying storage, there is also no need in doing like write-ahead logging. So we've seen several data structures starting from the B trees that are mutable, use no buffering, and use ordered storage. Then we tried to add in-memory buffers, and it had a positive impact on write amplification. Then with in-place update data structures such as WireTiger and lazy adaptive trees, we helped to amortize the costs of writes by combining them. You remember these little buffers attached to little nodes. In the immutable data structures, such as like LSM trees or FD trees or flash disk trees, we did pretty much the same at the cost of the future rewrites. So we kind of paid the price later rather than paying it right away. And so we only have to pay the write amplification price whenever we are compacting and rewriting the keys once again. And adding immutability in both cases had a positive impact on concurrency, but this is also known from the functional programming because like whenever you have an immutable data structure, it's just easier to manage it in the concurrent context. And some data structures such as copy on write trees showed somewhat larger write amplifications. And in immutable data structures, unless we buffer, we end up with unordered storage such as bitcask or bitcask or whisk key, which look a little bit like in-place update storage because of the reserved space. I think I said something wrong. In immutable structures, unless we buffer, we end up with either bitcask or whisk key. Or if we don't buffer, we end up with copy on write B trees, which look more or less like the in-place update storage because, I mean, their page structure looks almost entirely the same and they have to reserve the space in the nodes for the future reads and writes, even though they will be relocated in copy and write trees. And the BW trees is an interesting innovation here since they allow kind of best of the both worlds. So they give us all the guarantees that we possibly could have wanted. As you see, these three properties can be mixed and matched in order to achieve any sort of desired properties. As most of everything in computer science, the storage engine design is usually a compromise. So you increase the cost of one operation in favor of the other. And if you're interested in these things, in storage system design, in databases, I definitely recommend you to read a book. And if you are searching for the book, I can recommend you the book that I'm currently finishing writing. It's already available on early access program in O'Reilly, and it's going to be released hopefully in November. Yeah, and thank you very much, and that was it. I know that this is a lot, and this is somewhat different to process and digest, but nevertheless, I'm happy to take any questions. Once again, since this is kind of a packed material, I definitely recommend, there is a chapter in the book on each one of these data structures. So I was trying to give executive summaries and concentrate more on like these three concepts: immutability, buffering, and ordering, which you can use to remember where things sit. So, and I don't expect you to remember each one of the data structures, but these three concepts are important. Once again, just try to grab a book or grab all the papers, and I mean, because this is public information. And if you have any questions right now or during the 2 days of the conference, I'm happy to take them. Anybody? Yes, please? Yeah. Yes. So it is the team, as far as I remember, the team from Microsoft came up with it, and I don't remember which version of the Microsoft server is using it. If only we had a person who works in data or in Microsoft in the room, and they could answer this question. I'm just joking because it is used, and at least one more implementation that I'm aware of is called SLAD. It's a BW3 inspired implementation which is written in Rust. You can find it under spacejam/slad on GitHub. Anybody else? All right, we can just relax earlier, I guess. Thank you very much.